Enjoy. Thank you, everybody. And as you can tell, I've been in the industry a long time because I've got no hair and I've got a grey beard, so it's a telltale sign. All right, so what we're going to talk about today is this crossover between IoT, which is the Internet of Things, and AI. Now, I generally don't like to use the term AI, but everyone understands what it is. Really, what it is a couple of things, and we'll go over those definitions first. So the Internet of Things really is sort of a loosely coined term, and it's really an evolution of machine to machine, which came out of that cellular, SCADA kind of connecting devices space. It's been around for 27 plus years. And today it's probably more widely recognized as sort of the path of flow from a sensor through a network to somewhere. And the somewhere today is a bit different depending on the type of network it is and the type of platform it's going into. But basically, at some point it's transitioning from physical technologies, radio, LAN, to APIs or similar. And so the reason we do this, though, is that we want these sensors, which are now much, much lower cost than they used to be, trust me, to give us a lot more meaning and insights into business processes and processes. And AI, well, essentially AI is really a bit of a misnomer for what is machine learning. And machine learning really is a subset of algorithms that are applied across data. And in particular, what machine learning really is about is it's a form of advanced pattern analysis at its most basic level. And that's taking lots of data from different sources that generally has a pattern or perhaps what doesn't look like a pattern initially, and processing it with specific algorithms to produce something that is meaningful with pattern recognition at its most base form. And if you look at neural networks, visual neural networks, there's lots of different types of neural networks, but essentially they are taking what looks like data that is difficult to determine patterns from and running it for a model specific in a problem domain to try and produce some predictable outcomes from pattern analysis, pattern recognition. Now that's a very simple definition of basic machine learning, which is what is often termed as AI as well. So the data that goes into this AI process, this machine learning process, has to come from somewhere, and that's why there's a connection from the IoT side to the AI side. In order to get this data into a machine learning model to have some useful outcomes, we have to get it from a physical object somewhere into some software somewhere. And so it's a very important part of the IoT arena, particularly going forwards as well, because it's really meaningful insights that we want out of these two definitions that we've just gone through. So important in this as well is something called digital twins. So this is the concept where we have a physical object which is connected, it's measuring specific things we think are important around it, and bringing that same information back into the digital domain. And not only is it doing that in that direction, it also means that if we apply a change in the digital domain, the digital twin, that the systems we have in place, the IoT systems we have in place, apply that back to the device. So it's control and command through that reverse process as well. So digital twins contain not only data flowing backwards and forwards, but also metadata going backwards and forwards. And metadata is describing some state about the object that's not necessarily anything to do with the sensors, providing some inputs on the object, or outputs in the case of control. So essentially, changes that we propagate through this IoT network are affecting both sides of these digital twins. And so where that traditionally has been applied in the past few years is in high-value assets like turbines, because they have sufficient enough value as an asset to go to this effort to make this happen as an IoT solution to a problem. There's many, many different types of IoT networks. So this is a snapshot of what we have right now today to go out and buy, and there's some more coming online, which I'll talk about in a second. So at the very top end, we've got LTE Advanced, which is a cellular high-speed network. And you'll notice we talk about CAT numbers down here. That's part of the standards, Category 6, Category 5, Category 4 is part of the cellular standards. So that's today giving you 1 gigabit per second speeds, and it does that for a number of different mechanisms. Your phone, for example, using LTE-A, uses multiple spectrum at the same time to give you those kind of speeds. So multiple different radio bands that are licensed bands. And Cat 4 LTE is probably a bit more what we're familiar with because that's in most of our phones today. That's around the 100 megabits per second speeds. That's what the phone's capable of, not necessarily the network. That's a whole different thing. And of course, then we go down the chain and we're getting into this IoT space where it's more applicable. And the costs go down as well. So LTE Cat 1, we're looking at about 10 megabits per second. And then we're getting into these other technologies down here, which we call low power wireless area technologies. And they're designed for machine IoT devices. And so LTE M1 gives you about 360 kilobits per second. And this is where the metering companies are very, very interested in for smart metering, because it's just enough speed for them to put Bluetooth and Wi-Fi into the meter to do some smart home stuff, but not pay the full-blown costs, the cellular costs, with their fleet of 200,000 meters. So it's shaving the costs right down to the optimization point with that technology. NB-IoT is, again, it's a very constrained cellular technology, and it's about 40 kilobits per second, and that's designed for smart water meters. And that technology is good for battery-powered cellular devices to last maybe 10, 11 years. So if you have a water meter in the ground, that's the kind of cellular technology that's suited for that use case. Now, so far, everything we've described needs a SIM card or something similar to a SIM card in that device to connect to that operator's network. The next two down is actually unlicensed spectrum. So they're not licensed like a typical cellular network. And these are very, very good for low power devices as well. LoRaWAN is designed to be about 5 kilobits per second, 14 kilometer ranges, and it's very low cost. So you can set up your own LoRaWAN network for probably under $1,000. It'll cover 14 kilometers. So that's the kind of cost for the hardware in that space. And Sigfox is a proprietary French company's technology, but it's run by regional operators. And that's designed for very long-range, low-power devices as well on unlicensed spectrum. So in New Zealand, you're looking at 920 megahertz-ish, which everybody can use if they want to within some rules. And so it's all shared in those lower two comms types. So there's a big variance there. And what we're going to talk about next is what's coming with 5G. And I'll talk a little bit about 6G as well. It's not a myth. It is happening. Okay, so there's a lot we could go into around the low-power unlicensed technologies, but I'm not going to focus too much on that here because there's a lot of material freely available on that. In the cellular space, we're probably going to see a lot of commercial solutions use cellular low power to scale. And the standards that sort of define what happens in devices, battery-powered devices in that space, really is focusing on two of these standards we talked about before. One's Cat M1, so this is around 300 sort of kilobits per second in reality. And the other one is NB-IoT, or Cat MB1. And for those of you who are a little bit technical, you can see some of the parameters of these. So M1, you can do voice over LTE, you can send text messages with. So if you have a device that has those needs in a hospital or a PAL, you want to be able to do push to talk, Cat M1 will do that at a much lower cost than a traditional cellular device, for example. And NB-IoT, which is even lower cost because it's a simpler form of radio on silicon, doesn't support texting and it doesn't support voice, but it's very, very good at getting the message through. So it has very good propagation characteristics. Great if you're a water meter buried in the ground or in an understory car park or a basement or something like that. Okay. So there is a roadmap with cellular standards, and it's governed by this body called the GSMA 3GPP body. Now, if you're in the telecoms industry, you're going to get inundated with 3- and 4-letter acronyms. There's just no way to avoid that. So the standards body for cellular is those two entities, the GSMA 3GPP standards body. And universities participate in setting those standards, as well as commercial entities, and they come together and form the next iteration of standards. But effectively, they are numbered. So they're numbered in the form of this thing called releases along the bottom line here. So release 14, release 15, release 16, and soon release 17 are the standards releases that people then go away, the Nokias, the Ericssons, the Huaweis, and build some software that run the radio network from. So they don't do that until the standard is ratified, normally. And so we're kind of stuck between release 13 and 14 in the mobile network today. And so the standards, the features in those standards is what we get offered to us today. But what's coming is, in the IoT space, there's a lot more features that are fit for purpose for IoT devices. And I've got a couple up here, such as multicasting, which is where one cell tower can send a message to 10,000 devices. And if you're doing firmware over-the-air updates for security reasons, because security is important in the space, that's a crucially important feature. And so we can't do that today, but we will be able to do it when everyone implements release 14 in their mobile network. And as we go through this chart, you can see here there's more features coming in each of the release drops that support functions that are specific to IoT, the Internet of Things with cellular devices. And eventually, we'll talk about it in a minute as well, we're getting into 5G land, which is called NR, or New Radio. And 5G remains backwards compatible with LTE we have today as well. So the things we implement on 4G today will be backwards compatible as we go to 5G. There's been a lot of effort to make sure that happens. So looking at this cellular space and how we go to 5G with devices, what's coming is we're going to allow, well, the standards are going to allow devices to send on multiple different kinds of frequencies. So that's going to be important for spectral density, to get more devices working around a cell tower. Probably more so in larger high-density cities where you've got 20-story apartments. Each house might have several sensors in it. It's those kind of scenarios that need this support. The other one that is in the middle here is basically allowing a cellular device to behave as if it was a Sigfox or LoRaWAN unlicensed device, to send a message at any time without the network having to be synchronized with it like our phones are. You may not know it, but every one of you has a phone turned on now. Every 10 milliseconds, you're talking to the nearby cell tower saying, I'm here, I'm ready, I'm here, I'm ready. Every 10 milliseconds. And in some cases, that might be relaxed a little bit, depending on the network provider. But that's a lot of chatter just from this room to the cell towers nearby. We can't do that with battery-powered devices. So these features are trying to solve for a different problem. And what's coming in 5G, at the far right-hand side here, that's also come out of the emergency services part of the 5G standards, is the ability to have IoT devices talk to each other, like a radio mesh, and just have one of them talk to the network. So that supports even higher densities as part of the 5G standards. Now, the question you might ask is, so when is it going to be here? 5G sounds like it's going to be a long way away for these kind of scenarios. Well, I can give you a clue. There's a couple of companies who are releasing 5G IoT modules at the end of next month. So we're almost on the cusp of testing this stuff. So it's very, very close. They're not the only networks we can play with, though. What's emerging recently, thanks to effort from people like Rocket Labs, who are based in New Zealand, is this low Earth orbit satellite IoT networks as well. And so these are basically CubeSats. They're launched at very low cost as part of secondary and tertiary payloads from main payloads. And there's a couple of companies here that stand out who are doing early launches and testing in the space, or early network commercialization in the space. And one's Mariota from Australia, Fleet Space from Australia, Swarm Technologies from Mountain View, California. A couple of ex-Google execs have formed that one. Heber, based in Amsterdam. And we've got the big suspects, which is Elon Musk's SpaceX. Amazon are doing some work in the space. OneWeb, Lacuna, that's another Dutch initiative based around using LoRaWAN technologies to go to space. And Starlink is the ultimate 6,000 low Earth orbit satellites surrounding us, giving us broadband-like speeds with lasers between each other. I've seen a great 3D model, and I don't hold my breath for it being here in the next decade functionally, but you never know. So as we go through this way, basically, the low costs here are really driving this to be a valid IoT solution for remote scenarios. So I have 2 development kits that just arrived last week for 2 of these companies that allow me to go out next week and actually test an IoT sensor in a remote part of New Zealand if I need to. It'll send 1 message a day, but it's enough for testing in some use cases. And as they put up more and more of these CubeSats, that messaging rate will eventually come down to 1 per 5 minutes is the rate you could probably apply if you wanted to. The CubeSats themselves are very, very small. The Swarm Technologies guys, imagine 3 pieces of toast. That is literally the size of their CubeSat, and that's enough to do the job. Now, they do go around pretty fast. It's 400 kilometers low Earth orbit, and so they are going around 10, 15 times a day, but they don't go around the same orbit. So although that sounds great, we've got some other things to deal with around actual coverage in a given zone and area. But you can go and buy dev kits from 2 of these guys, 3 of these guys, and actually get involved in this if you want to. So we've got no shortage of networks. We've got devices that can send no shortage of information. But is it the right thing to send it across the network? In some cases, it's not. If we think about accelerometers, you've got 3 axes producing a lot of information every 1 millisecond or so when you vibrate to the device. An accelerometer detects vibration on the XYZ axis. You don't just want to send that all across the network raw, because you're going to need a lot of bandwidth. And so we have to do some processing and signal processing to manage that kind of information density. And traditionally, we might have just done a simple compression on that, or maybe detected a couple of event thresholds on that vibration pattern. But what we can do now, with the change in cost and computation and sensors, ARM processors, RISC processors we have, very low-cost microprocessors, we can actually start to apply machine learning on the device itself without impacting battery life, and effectively emulate what we can do on much larger computers with the machine learning model. So essentially, we're now moving the intelligence to the device through new frameworks, lower power processors, to do this analysis of these sensor telemetry in the device itself. And so that essentially is effectively running a neural network on battery-powered devices. Now, there is a process to this. You develop the model in your larger PC/application environment. You test and simulate the model, and then you compile the model down to be ready to go onto the device. So it's the model that goes to the device with a runtime that allows us to do this machine learning on these very small battery-powered microprocessors. And so if we think about that, I mean, here's an example here. This is a pin. This is an accelerometer. It's a MEMS accelerometer, and you can see how small that is. So when you can start to pack that kind of density into telemetry inputs on sensors, to be able to do the machine learning, the signal processing on the same device starts to have a lot of meaningful impact on the product. You're not having to choose the most expensive network with the highest burden cost with your IoT product, whether it's industrial or consumer. So processing at the edge is a thing. And there is a graph here, which is a chart between compute and radio transmission as a power consumption on the device. So what this chart shows is the machine learning power consumption versus the radio power consumption. And you can see here that, even with Bluetooth, we've already gone above the power required with these new machine learning frameworks to run on this device. And you can see if we go to cellular, we're going to use a lot more power of cellular radio. We're transmitting that information all the time, rather than just processing it with the machine learning framework on the device itself and only sending what's summarized or what's interesting from that accelerometer, for example. So how does this happen? Well, it's really about a couple of new frameworks that have good work that's come out of Amazon and Google and the big players. And these are frameworks, software frameworks that are machine learning frameworks, like TensorFlow. So there's TensorFlow that's been in the cloud space and in the PC machine learning space for a while, and that allows us to do neural networks on bigger compute. TensorFlow Lite is the evolution of that, or what's come out of that, to allow it to run on these constrained battery-powered devices. So there's a process here, and that basically is to develop the model, compile the model, and then put it onto the device as a module. That's a machine learning module, a neural network, if you like. And then we can send the summarized events only to the back-end application server. So really, this is the age of tiny ML. And so this is happening now in new product development as we speak. Because some existing microprocessors in an existing product, cameras, stuff like that, can do this purely with a software change. And an example here is, we've got an accelerometer doing anomaly detection and neural network NN classifiers, which is basically looking at, in this case, the graph shows an accelerometer looking at X, Y, Z movement on a body, in this case on a human body, or a machinery, a pump, a large pump or some machinery, and then building this model which is showing the normal classifiers, the normal operating state, and then when that deviates, a bearing starts to burn down or a person falls over and doesn't come back up again, those are outlier states in this model that we can then react to directly on the device. So the cloud system doesn't have to be aware of that processing until we strike an outlier condition running on this battery-powered device. And an example here is one of these little processors, Cortex processor. It just takes 6.6 kilobytes of RAM and 20 kilobytes of flash to do this with an accelerometer. That's a very, very small amount of memory and storage required to do this. So you can get a sense then that AI is going to become very important in the IoT future. And in fact, the two things are going to become blurred and merge. And it's coming already from the industrial space because these high-value assets, no one wants downtime on them. So you really want to know in advance, predictive machine learning, if you need to do something, schedule a service window on that gas turbine or that pump, water pump that the city council might be using, for example. And so by combining traditional IoT with AI, we add another dimension, which is the ability to act on these prior abilities, which is collect and store and process and control. So the ability to act is getting closer to the decision-making process that we as humans might make through insights from this information. An example of where this is. Today, you can go out and buy any one of these hardware kits for around about $20 to $120 from a website, and they will give you a machine learning framework to start to experiment with and test these out. These are particularly focused on cameras. So with these cameras, you can do things like facial recognition, object recognition from your model, and you do have to spend time curating the model. There is a human still required in the loop here, by the way. And something like this bottom one here, this is a $200 LiDAR sensor. So it's come out of the car industry, the automotive industry, but there's nothing to stop you developing a product to put on a vehicle that looks for people in an area they shouldn't be in. An example here is a construction site. If you're in the construction business, the roading business, you could quickly develop a sensor that told you that you were backing a vehicle into a human body and do something about that in the processing capability on that site. No cloud involvement required in that scenario. So there's a lot of emerging scenarios with this low-cost machine learning that's coming to the IoT world that allow people to open new opportunities to develop products very, very rapidly. Number plate recognition. Instead of using traditional parking columns where you have to do a lot of interaction, you could have one of these cameras automatically recognize your vehicle, do a query to NZTA, find the details, confirm it on your phone, and walk away as a process if you wanted to integrate that. So there's a lot of things you could do through automation from this type of low-cost access. And here's an example of a camera that runs purely on a solar panel. It doesn't even need a battery. It's got just enough processing power in the FPGA chip to do recognition on objects within a small confined space. So there's a lot you could do with this kind of stuff that also doesn't require solving the problem of battery chemistries, battery energy management as well. So this is how little power AI at the chip level is using. So, shrinkage. So semiconductors are shrinking. I thought I'd introduce you to an example here of where that's going as well. The Michigan moat was developed by the University of Michigan, and its first iteration was the top photo here, which is the size of, I guess, probably a good chunk of a good rice grain, a good large-sized rice grain. And you can see here that the second iteration has shrunk even further. And so when we combine what I just talked about, the ability to do machine learning on something that size, you can start to see where this is going in terms of advanced features coming to very, very small electronics. And this particular one has solar power and has a number of other functions, as you can see from the breakaway here, to power it as well. is a single grain, if you like, of compute power that can run these TensorFlow-light machine learning networks. So this is all exposed in the consumer space, so you can imagine what's happening in the non-consumer space, right? Which I have done some work in, but it's another problem domain as well. This is another example of dedicated Ai IoT hardware. So this company, Sentient, has developed a chip that's specifically designed with its machine learning to recognize voice and understand speech, like Siri, like the cloud-based solutions we have. So this chip will run on 150 microwatts and will allow you to train a model to recognize human speech and language in a given voice. And so this brings the ability to interact with your common appliances. Your machine, your washing machine, your toaster, that kind of stuff is where this is headed. Your car, for example. No cloud connected. You run the model entirely on the chip, and it's consuming a very, very small amount of power. So you can go out and buy an SDK kit, a kit to start developing with this tomorrow if you want to. So we talked about standards and machine learning, and I guess out of this space, machine learning space, we are going to increase the size of the model at some stage. We want to do more complex machine learning models. Then we're going to require bandwidths to get the model to the device when we do updates. So this is where we need a bit more than 5G at some point in the future. And so 6G has been worked on as part of this domain. And in 6G, there is also IoT using 6G in the standards side of things. So 6G talks about a lot of high frequency, millimeter wave, terahertz, 100 gigahertz to terahertz stuff. And so 6G is really about speeds at its core, more speeds. But if you think about those 5G features, multicast, peer-to-peer, mesh-to-mesh, that will also come to 6G for IoT devices as well. And that's progressing quite fast. Here's an example of a chip that's been developed. It's 4 millimeters square. And that's giving you about 36 gigabits per second at 30 centimeter distances today. So you can go and buy a dev kit that allows you to play with this chip, if you can export it out of the US, and start to experiment with how this might work in a product, for example. Now, if you think about it, where would you use that speed? AR headsets, right? That's a classic case. Wireless AR headset, you need this kind of stuff, right? And the kind of signals we're talking about are in the terahertz region. It's traditionally been very hard to think about how we might manage radio at that speed, that spectrum. And we do that by lasers and graphene and using massive MIMO, which is lots and lots of little antennas. And we software beam steer the energy to where we want it to go to. So the device will beam steer the energy towards the cell tower or the radio that it's meant to interact with through these kind of concepts. Ultimately, 6G is going to lead to some pretty sci-fi-like scenarios. When you think about where we are today with brain interactions today, you've probably seen the videos where people can control rudimentary objects using ECG-like concepts. Well, ultimately, 6G is going to allow enough bandwidth with these types of sensors to allow us more direct interaction from the human mind with what's around us from an IoT perspective. And there's a couple of quotes here that suggest that by 2036, this will be affordable to people using this technology to have direct interactions without verbalizing it or being physical with the object. So it's where it could lead to and where it probably will lead to from that very simple concept of IoT devices is not too far around the corner. And probably our children's generation will see this start to come out in products at some stage. And I think that's probably it for me.
Thank you very much. So just a couple of questions. So what's exciting you the most? What's happening in the hardware or what's happening in the network?
Probably the combination of, to be honest, because they both require each other. If I think about features that the device requires, the network has to support them to make it complete. So if I want a battery-powered device to run for 10, 15 years, to go to sleep for a whole day, the network has to honour that request, and then the device will get on with managing that state. So the combinations of those things is probably where the sweet spot is.
Cool. And I guess it's one thing, I guess, the general public sees 5G and they think speed, but they don't necessarily understand all the extra connection points and things like that.
That's
and I guess,
correct, yeah.
What are the real opportunities for Joe Bloggs? What are they going to see in 5 years' time?
So with cellular-based connectivity, you won't see a SIM card anymore soon. It's going to become part of the chip. There's a company called Arm in the UK. You might know Arm. It's a well-known English company. They have it already. They sell intellectual property. They sell the designs for silicon. People make the silicon out of fab plants, factories. And they already have a design where the SIM is an eSIM on the chip. And the reason for that is to make the whole thing secure. So there's no chance of that SIM's credentials, its secure memory areas being tampered with in any way without destroying the chip.
Cool. Brilliant. Right, thank you very much.